I may not be that deep as much as you are, right? So I will run through all basic optical concepts, right? So starting with optical power, right? And optical power for me is how bright is this light that's hitting my face, right? It's the intensity of light, it's that brightness of light. And generally when we measure that brightness of light, we tend to measure it in decibels. And with regards to decibels, decibel is really good if you want to measure something big or something small, right? But then for IP folks, because now as IP over DWDM, all the other concepts come in, you start seeing those optical parameters on your routers and switches. So you need to know what those mean. So if you see something, so dB tells me nothing, right? It's just a ratio of two values, but ratio of what, it doesn't tell me that. So if somebody says, oh, it's minus 10 dB, generally it's saying it's 1/10 of something. If it's 10 dB, it's 10x of something. If it's minus 20 dB, it's 1/100th of something. And when you measure power, we generally tend to measure power in dBm, decibel related to 1 milliwatt of power. Because we need an absolute value, which means we need a reference value. And the reference value is 1 milliwatt of power. Which means 1 milliwatt is 0 dB. Right? Minus 10 dB is 1/10 of 1 milliwatt, 0.1 dB. And so on, right? So that's the first concept for IP folks. Second one is attenuation. If there was no mic or AV system, if this was a long hallway, as I speak, my voice fades. Right? Similarly, as you pump light into a fiber, over distance, it starts losing its intensity. It becomes less intense, less intense. So we generally measure that as loss per unit length, right? But why do we lose intensity of light? Back to fundamentals, physics says shorter wavelengths tend to get scattered, right? Some escape out of your fiber core, some might be reflected back to your source, and that is what you generally see when you use your OTDRs. People who use OTDRs, it's that phenomenon, that reflection that you see. With longer wavelengths, now remember our fiber is the glass, right? And we, to modify the reflective index of the glass, we generally add dopants, right? And some of those hydroxides or those dopants, they tend to absorb longer wavelengths. And it's that absorption that causes attenuation. So those of you who might have worked in transmission in the old days, you will see that when fiber optic communication started, we had this 3 low absorption windows. The 850 nanometer, the 1300 nanometer, and the 1500 nanometer. It was not just because somebody decided, because it was the lowest absorption. That's why we used to use them as our transmission window, right? Next concept, chromatic dispersion. Again, physics says different colors of light, which is different wavelengths of light, they travel at different speeds inside a fiber, right? Longer wavelengths have a very low refraction, which means they bend less, which means they travel faster. Shorter wavelengths tend to bend more, which means they travel slower. So if I send a pulse of light from here, by the time it reaches the distance, because the longer wavelengths tend to travel faster, shorter wavelengths travel slower, think of it like I tried to generate that image using an AI, right? I think I generated that before BTNO. Think of a very fast sports car and a normal car starting at the same time. By the time they reach the destination, the sports car reaches a bit earlier, the regular car reaches a bit slower. So that time difference is what we call chromatic dispersion. Chromatic dispersion for IP guys, you don't need to know depth, but know that the time difference of the different colors of light at the destination is what we mean by chromatic dispersion, right? What is the problem with this? The problem with chromatic dispersion is, as the light pulses broaden, they start overlapping with each other. So if I'm a receiver on the other side, I can't distinguish which one is the first pulse, which one is the second pulse, right? So for data transmission, we call that bit error. So chromatic dispersion, in summary, causes bit errors, right? One more form of dispersion, polarization mode dispersion. If I'm transmitting light in different polarizations, again the same phenomena occurs, where light in one polarization arrives before the other light. Again, the pulse is broadened, they interfere with each other, again it causes bit errors, right? The other way we measure signal quality in fiber optics, or even in the old transmission days, microwave transmission, it's signal to noise ratio, right? It's the ratio of your very good signal versus the unwanted noise that you have. Right? That signal to noise ratio. For IP folks, do you need to know depth? Maybe not. Just know that higher is better. Higher OSNR means the signal is very clear, which means there are less bit errors. Right? Today morning, when there was keynotes being delivered, coffee was happening, booths were open, the noise floor was quite high today morning. Right? The signal to noise ratio was very low today morning when we started the morning sessions because the noise in the room was quite high. Right? You don't want that, you know. If as your signal to noise ratio drops down, your errors tend to increase, right? That brings me to the next concept, bit error rate. Bit error rate is ratio of the error and the total transmitted bits, right? So when somebody tells you, an IP engineer, that, oh, the link is quite weird, the bit error rate is 10 power minus 9, what they're trying to say is, for every 1 billion bits I transmit, I expect 1 error. So that is how we interpret bit error rates, right? Like I said, your OSNR directly affects your bit error rate, right? The quality of the link, whether it's a terrestrial DWDM link, whether it's long distance submarine links, your OSNR dictates how much you can pump on a fiber, right? Higher OSNR, clearer signal, less error. Lower OSNR, very noisy signal. If I'm a receiver, I don't know how to decode the zeros and ones out of that signal, right? So it causes higher bit errors. Let's put things into perspective, how it causes those bit errors. Here is an example of a constellation diagram of 16-QAM modulation, right? Let's start off with a very good OSNR of 30 dB. If I'm a receiver, I see each point on the constellation clearly, which means me as a receiver, I'm able to decode zeros and ones out of that first, because the signal to noise ratio is quite high. Let's say the signal to noise ratio then drops down to 20 dB. Yeah, things are getting a bit smudged, but if I'm a receiver, I can still see the points on the constellation. I'm still able to decode information, right? But as the signal to noise ratio drops down to 5 dB, if I'm the receiver, it's all over the place. I don't know how to decode information, right? So this is how signal to noise ratio affects bit error rates, right? We humans are smart, so we come up with a solution. That solution is forward error correction, FEC, as we call it, right? IP guys, again, don't have to know so much detail, but know that FEC is just extra redundant bits that I transmit together with my data stream, so that you at the receiver, even if there are errors, you can use those extra hints to reconstruct the data I send you, right? Again, an AI generated image there, the old classic noisy telephone lines, right? If you were talking on that, think without FEC, it's very noisy, the listener doesn't know what you're saying, they'll ask you to repeat. And it happens in data transmission also. If I'm a receiver, I'll ask you to retransmit because I can't decode information. With FEC, I throw extra hints, right? Like in that image, the speaker is saying the car is blue, it's a blue car. He's repeating it, he's paraphrasing it. And then the listener, understands. Even though there is noise, I'm still able to understand what you're saying. So that is what FEC actually does, right? So in practice, forward error correction is important when you have a long distance link which might be noisy, right? It allows you, even if there are errors, it will correct the errors for you, and at the receiver, you're able to decode the information, right? Some quick concepts. Fiber links, whether it's submarine cables or terrestrial fibers, are very expensive investments, right? You don't want to just carry one data stream on a fiber, so you might want to carry multiple data streams on a fiber. So what do? We pump different colors of light. We call them wavelengths, right? And each wavelength is independently carrying different data streams, so you have increased the capacity of your fiber. Typically, we have CWDM, right? Coarse, broad spectrum. Problem with broad spectrum, doesn't play nice with amplifiers, right? That's why with CWDM, you can't really go far, right? It's good for a shorter distance one. Hence, we come up with dense spectrum, we come up with dense WDM, where I'm finally able to go longer distances, right? I can carry more channels in it. C-band is almost exhausted now in DWDM,
L band is being discussed, but you might have to replace your filters, your amplifiers if you want to go into the L band, right? Problem with the DWDM that I mentioned earlier, we call them the fixed slot DWDM. The problem with that is you waste a lot of your spectrum, right? If I have a, let's say, an example, a signal which is 36 gigabaud with your guard band, I think it fits perfectly into a 50 gigahertz slot. But if you have a very narrow signal, a low gigabaud signal, you're wasting a lot of your spectrum. If you get a bigger signal, which could be 100 gigabaud or more, which is what we use in high data rate, your 100 gig, 400 gig optics, then I don't have enough slots in that 50 gigahertz fixed DWDM. So we go with what's called flex grid, right? You give up on that fixed grid idea, you split it into multiples of 12.5 gig. If you have a bigger signal that's coming, give it multiple slots. If you have a smaller signal, just give it few slots. You don't waste any of your spectrum. So that's flex grid. Now back to your engineering days, right? Maybe this will take you back to school. We think we live in a digital world, but sadly we still live in an analog world, right? For me to carry data from point A to point B across Mongolia, either you do it over radio, you do it over fiber, I need to encode that signal into either optical wave or into a radio wave. And remember, light is an electromagnetic wave, right? Light has fluctuations of electrical field, which causes magnetic field, which causes electric field, and so on. Hence why it's called electromagnetic wave, right? So for me to carry digital data from point A to B, I need to encode that into an analog wave, carry it across a link, decode it at the other end, right? So as IP engineers, if you hear the word baud rate, so baud rate is nothing but it's the speed at which I modulate a signal, right? So if somebody says, oh, it's a 10 gigabaud signal, what does it mean? For IP guys, I'm flashing the torch 10 billion times per second. That's what you mean by 10 gigabaud, right? So these are concepts you still would need to know. So now you know baud rate, you know fundamentals of optics. So how do we get our data rate, the bit rates, right? Unlike radio, in the radio world, me as a microwave engineer also, we used to use very high order modulations those days. But in optics, it started with a very simple modulation technique, encoding technique. It was called IMDD, right? Intensity modulation direct detection. Intensity meaning I only modulate the brightness of the light, the amplitude of the light. Direct detection meaning I have inexpensive receivers or photodiodes that only know how to detect the change of the intensity, right? So it started very simple. Some people also call it non-return to zero, NRZ, or amplitude shift keying, call it whatever you want to call. But the idea is high level voltage, a higher voltage or a higher amplitude was seen as one, a presence of light, or absence of light, we interpret that as zero. Which means with NRZ or IMDD, I'm able to encode 1 bit per symbol, right? 1 bit per symbol. So if I have a 50 gigabaud signal coming, because I can only encode 1 bit per symbol, I can achieve 50 gigabits per second. So that's how we build optical transceivers, right? So how do we achieve higher bit rates? How do I go to 100 gig? How do I go to 400, 800, 1.6 terabits? How do I achieve this? Do I just keep increasing the baud rate? You saw that with 50 gigabaud, I could get 50 gigabits. So do I go 100 gigabaud, 200, 300? Problem with keeping increasing the baud rate is dispersion starts affecting a higher baud rate signal, right? And if you want bigger baud rates, I need more spectrum. And spectrum, you eventually run out of spectrum. So what do? How do we achieve higher data rates? I can't keep going crazy with the baud rate. So we are again smart people. We say, okay, let's go back to basics. Can I encode more bits per symbol? Right? So you then start looking at higher modulation techniques. In this example I have here, remember in NRZ, presence of light was 1, absence of light was 0. I could only encode 1 bit per symbol. So with PAM4, for example, pulse amplitude modulation level 4, I have 4 levels of amplitude, right? Which means I can now encode 2 bits per symbol. So with NRZ, I could only encode 1 bit per symbol. With PAM4, I'm able to encode 2 bits per symbol. So for the same signal that I had earlier as an example, 50 gigabaud symbol, because I can encode 2 bits per symbol, I can now achieve 100 gigabits per second. So just by changing the modulation technique, I'm able to double my data rate, right? So do you just keep going crazy? No such thing as free lunch. I don't know, for mnNOG, you got your lunch because you registered, right? You paid a fee. Maybe some of you got free lunch, but in life, there is no such thing as free lunch, right? If you compare the eye diagram of NRZ to PAM4, just because I want to encode one extra bit, you see the signal amplitude is just 1/3 of what what NRZ is. Problem with the smaller signal amplitude means it's more susceptible to noise. Noise means lower OSNR. Lower OSNR means higher bit error rates again. So with PAM4, you really can't go longer distances, right? So we're again back to the drawing board. How do I achieve higher data rates, go longer distances, right? Back to physics. Again, you go back to fundamentals. Light has more than amplitude. Light is an electromagnetic wave. It has more properties, right? And if I can encode data into those different properties of light, I can carry more data. That's the whole idea, right? One such property of light is what we call phase. You don't need to know details, it's just where it is in its cycle, right? If you look at that wave, where is the wave in its cycle is what we call phase. So if you look at those two waves, the green wave is shifted or off from the blue wave by maybe a quarter of a cycle, about 90 degrees, right? If a full cycle is 360 degrees, it's off by about 90 degrees, right? It's phase shifted by about 90 degrees. So, can I use the amplitude and phase shift to encode data? Yes, we can, right? And as we do that, that's how we manage to increase the data rate of the modern optics that we do. And if you have heard the word coherent optics, it actually borrows this from this phenomenon of wave, right? Waves are known to be coherent if they have the same frequency and if the phase difference is constant or steady, right? So, now that we are back to basics, let's use the amplitude of two carrier signals that are phase shifted by 90 degrees. We want to use both phase and amplitude of light to encode data. One such example is 16 QAM, quadrature amplitude modulation. If you look at the constellation diagram, you now see 16 different amplitude and phase angles in that diagram, which means I'm now able to encode 4 bits per symbol. Remember, IMDD, 1 bit per symbol, PAM4, 2 bits per symbol. With 16 QAM, I'm now able to encode 4 bits per symbol, right? So going back to our bit rates, with on-off keying, which was your NRZ, you could only encode 1. PAM4, you could encode 2 bits. With 16 QAM, I can encode 4 bits. Now, just by increasing the order of modulation, I'm able to effectively double the bandwidth, right? Because with PAM4, I could only achieve 100 gigabits with a 50 gigabaud signal. But with the same baud rate, I'm able to achieve 200 gigabits just by playing with the modulation. So do we keep just playing with the modulation, then keep going crazy with the modulation? We have to revisit some fundamentals again, right? If you look at a constellation diagram, that spacing between the constellation points in that diagram is how immune are you to noise, right? And that point from the constellation point, that distance from the constellation point to the origin is how much power is needed, right? How much power does your optics consume? So let's compare 16 QAM and 64 QAM. If you want to maintain the energy of the constellation to be the same, if you compare those two now with 64 QAM, which is a very higher, it's a higher order modulation compared to 16 QAM, you see that the points are now closer to each other. They're very close to each other. What does that mean? More noise. More noise, lower OSNR. Lower OSNR, again, bit errors, right? So you just can't go crazy with modulation either, right? But radio guys or all the mobile guys, if there are mobile guys in this room, you might say, oh, 4G we do 64 QAM, 5G maybe 256 QAM. You really can't go far, can you, with your 5G? Can you go 1,000 kilometers? Because of noise, right? Wi-Fi 6 does 1,024 QAM, but Wi-Fi 6 is good in a room. It can't go beyond that. So that is the problem, right? As you go with higher order modulation, you are restricted on how far you can go, right? So we again go back to basics. Okay, I can't go far, I can't go crazy with modulation. So what do? Again, go back to basics. Light has more properties. We only use amplitude and phase. There's also a property of light called polarization, right? And polarization is nothing but it's the direction of your electric field, right? In this diagram example, the electric field is on the vertical. So we call it vertically polarized optical wave, right? Before I talk optics, we do use concept of polarization in real life, right? I live in Australia. There are a few of us from Australia here. It's a very sunny place. We use sunglasses. Even today, when going for lunch, I saw some people with sunglasses. Why? When your sunlight hits a surface, the light that it reflects back to me is horizontally polarized. So your sunglass blocks that out. It only allows vertically polarized light. So that's how you wear sunglasses. Same with your 3D movies, right? Your 3D movie glass, one side only arouse vertically polarized light, the other one only arouse horizontally polarized light. Two sources of light hits me, and my brain thinks it's a 3D image. It's not, right? It's two different sources of light. All fun, but in optics, instead of sending data stream only in one polarization, I can send it in the other orthogonal polarization, 90 degrees, which don't interfere with each other, right? Brilliant idea, we can double the bandwidth, but if you look at that animation on the right, if I'm a receiver, how do I decode information from that dual polarized 16-QAM signal, right? I cannot. Not with my direct detection receivers that can only detect a change of the brightness of the light, right? So we then have to come up with a different set of receivers called the coherent receivers, right? With coherent receiver, I have a laser on the receiver side, right? Oscillator, and the reference signal from that receiver I mix with the incoming signal, and I extract the phase and phase and amplitude per polarization, and then I feed it to a DSP somewhere, right? So now visiting our bit rate. Remember, our bit rate previously was a function of baud rate and modulation. But if we are able to use polarization, now our bit rate is a function of baud rate, modulation, and the polarization. So with the same 50 gigabaud example that we had, run it through a 16-QAM modulation, you encode 4 bits, you get 200 gigabits per second, run it on dual polarization, you achieve 400 gigabits. That's how we built 400 gigabits optics, right? No magic, it's all basics, right? It's all back to basic and fundamentals. But in reality, of course, 400 gig Ethernet is not 50 gigabaud. We have about 60 to 61 gigabaud signal, which means in the end, I achieve about 480 gigabits per second. For Ethernet, I need about 425 gigabits for a 400 gig Ethernet. The remaining 55 gig is an overhead that is required for your FEC, your forward error correction, for you to do bit error corrections. DSP does magic. Of course, it consumes a lot of power too. So DSP is what helps me encode data into phase, amplitude, and polarization. It does all the error corrections. And most importantly, it does dispersion compensation. So your old fibers in Mongolia, Bhutan, pretty much anywhere in the world, the old G.652D fibers, they were put in 20 years ago, 30 years ago. And our problem in the old fibers those days without coherent optics was always dispersion. So you couldn't go much further, you couldn't push much data rate, but now with DSP, it even does that compensation for you, so you don't have to pull new fibers. You can reuse your old fibers, give it a new life, right? For IP folks, that last line is for you. You don't have to know what DSP is. Like I say, I treat it as a noise cancelling headphone that can do auto correction for you, right? So that brings us down to how we built modern coherent pluggables, right? The old days we had transponders as big as a laptop. Now we have something as small as a clicker, right? Which consumes way much less power, right? Moving on because I'm running out of time. So what happens with the modern coherent optics is because you can plug them into routers and switches, you now start seeing all these optical parameters on your router management plane. Right? In the old days, you have to wait for the transport to fail before your routers detect it. Now you don't have to. I can see all the optical parameters on my router or on my switch, which means I can react faster, right? Which means I can move from something like this, which is a very classical DWDM-based network where we run our IP on top of a transport network. We can now build a consolidated, simplified network where this optics directly go into my routers and switch, hence why we call it pluggable optics. And we are finally able to build a routed optical network, right? And this is what we mean by IP over DWDM, right? And that's how now you're able to consolidate, simplify your network design. No more separate transport, no more separate IP network. You have a consolidated IP over DWDM network. And you think I was lying? No, we did a massive workshop with DKIX in Frankfurt where we were actually testing out IP over DWDM with DKIX in Frankfurt. And if you want to listen to the talk, it was presented at mnNOG by my CTO, Thomas, right? Thank you, that's my talk.